Good day, welcome to part 3. We're going to be talking about some science communications. Basically, how do we talk with each other and how do we get science done? It's a lot of writing. Okay, for starters, we're going to have to share information. This was, once again, the core part of what Lord Boyle had done. He had made it so his work could be shared and builded upon by others readily, as well as checked. And like the pure and applied divide, there is a divide on how we share information because different scientists have different goals. Industrial chemists, as well as in general industrial sciences as a whole, aren't trying to share their information with the world. They're trying to share with their company and people working for their company because obviously if you're trying to discover a new drug, you don't want to tell your competitors how to do it first. Also, you want to be fast. Time is money in business. So generally speaking, industrial chemists are going to be doing a lot of work with memos, very short 1-2 page documents that document what they've done, the results of a single experiment. And then they're also going to be looking at patents. And patents are actually a huge deal. One of the revolutions in the 19th century wasn't just we could figure out how to make money, but it was the development of intellectual property laws. Patents are legal documents that tell the whole world how you did something, with the caveat that no one can do it without your permission and giving you money for a period of time. For a patent, it's usually around 20 years. Obviously, things vary by country, by, laws change all the time. But around 20 years. Now, academic chemists don't have that same scenario. We want to share what we're doing, and I say we because I'm an academic chemist. We want to share with our community so that they can build off of our work and we can build off of theirs as well as, bask in the glory of doing, hey, I did some minute thing. So we're going to be sending and doing what we call peer-reviewed research papers. So they're going to be longer, a couple of pages usually, multiple experiments. They have some kind of narrative, something like, we discovered this, 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 and this means this kind of narrative. But they're also going to be reviewed. An industrial chemist, the real, where the rubber meets the road is, do I make a product that works? And if I don't, my company's going to get rid of me. But an academic chemist, if you're model building, we want to check to make sure the model works. And I could add something that's complete garbage, and if no one checks, no one would know it. So the goal is we have peer-reviewed. Before that paper gets published and sent out to the world, it gets sent to about 3 individuals who do about the same thing that I do. And they read my paper and make sure it's not total rubbish, hopefully at least. Now, I should point out that industrial chemists do write peer-reviewed research papers. Academic chemists, we also do a lot of conference talks, or a moderate amount, where it's basically the same story as the research paper, but we go to a conference and we say, here's what I'm doing. It's usually a little bit more at the moment, much more timely. Industrial chemists will do that as well, quite often plugging their whatever device. And academic chemists will definitely write patents. Here at Georgia College and State University, we just got a patent last year for a device that measures the flow of liquids through pipes using sound. And it's going to be a pretty sweet patent. There's probably some cash flowing into the university from that one. At least we can hope. So we do both of these, but generally speaking, industrial chemists are focusing on the memos and the patents, and academic, we're really focused on those research papers and hopefully a conference talk or so. Quite often it's, one conference talk, then it comes out as a paper, and, kind of back and forth. Now, that peer review is a big deal. So the general idea is once I write up or somebody writes up a paper, they submit it to an appropriate journal. And there's all kinds of journals, and essentially they're just publishing companies, same as like your magazines, etc. But they work a little bit differently. First, there's an editor. They look at it and make sure it's not complete rubbish, and sometimes they just chuck it right on the trash can because it's like, I don't care about that. Or also, it's like you've got a research paper on Brazil nuts, and this is an petroleum products journal because they're specialized. I don't care about Brazil nuts, so send it to somebody who does journals on Brazil nuts. So he's going to look over, make sure that, he or she, whoever's looking over this paper, like this looks pretty good. Then they send it off to some other researchers who generally have a better idea. The editor may have no idea what you're reading about. So they don't necessarily know if you're coming with a bunch of malarkey that's already been disproven or what's going on. So they send it off to some other researchers, usually about 3, and they're almost always anonymous. And they look at it. It's like, oh, hey, how's this look? And the reviewers send back their comments like, hey, this looks great, or boy, this is badly written. But, it looks interesting, or, you get some review. And then the editor is like, okay, we'll publish it. We'll usually send it back to the original author to fix problems that were found. And or just says, forget it. Hopefully everything succeeds. It goes on to the publication, goes onto their website, goes out in print occasionally. That's dying, obviously, like all other print media. The author pays a fee for the editor to review it. The readers quite often pay a fee to read it, and thus the journals make their money. Quite often, if it was funded by government money, there's stipulations that the journal has to provide the paper to everyone for free, electronically, obviously, after a certain period of time, because, the taxpayer paid for it, the taxpayer should be able to read it. And that's hopefully how things work. People read papers, get an idea of what's going on, etc., and hopefully everything works well. Now, papers come in a few different types. What I basically described was a primary research paper. Researcher goes into the lab or sends their assistant into the lab. They do a bunch of experiments. Probably about 6 months to a year worth of work gets summarized up in maybe a 4-page paper. Kind of depressing when you think about it that way. Some folks are able to knock out a paper every couple of weeks. Some folks, 1 paper in a 5-year period. I'm one of those. That was good. I got my 1 paper. Yeah. But this is cutting edge research. It might be particularly not that interesting, but it's still cutting edge of something. Now, another form is the review article. And a review article, quite often a researcher will summarize all of the primary research papers that have been done in a field. Or, a few of them, the important ones, the ones that researcher thinks are good. And the goal here is to take a bunch of small steps and put them together so we get a better understanding of what's going on. Now, review articles sometimes they're great, sometimes they're not, sometimes researchers might cherry pick, etc. So the next level up for a review article is a systematic review. It's a slightly higher quality review article. In this case, the researcher doesn't just pick the ones that they think are the best. They pick all of the research papers that meet certain criteria, and they tell you what the criteria are. So published within these date range, had an experiment that met these quality standards, that kind of stuff. And they summarize all of the papers that meet that quality. That way the researcher didn't cherry pick. There was a bit of a scandal, more of a discovery of a bit of a controversy. Of the 60s, a review paper came out and said that the research had shown that fats caused heart disease. Well, it turns out that paper was heavily cherry-picked, and really there was a lot more emphasis that should have been focused on processed sugars. Systematic review eliminates this issue. The next level up from the systematic review is a meta-review. In this case, the researcher not only takes all the papers that meet certain criteria, but then takes the data from those papers and combines that data together and statistically reanalyzes it. This is particularly useful when you have something that has a very small or very noisy effect, where you're not really sure what's going on. You know something is important here, but you've got some papers that found some findings and some papers that disagree. So if you've got fairly controversial areas, a lot of things like nutrition, once again, it's really hard to do a good nutritional study, so it's really great to have meta-reviews where you're taking a bunch of studies, you're taking all the information there and you're statistically combining it, so now all of a sudden you get a much better picture of what's going on. Now, when you read a scientific paper, you can do it. And this is one of the things that, folks something like, oh no, it's too hard. No, you can do it. So if you want to jump into the scientific papers, you can do this. Now, what you want to do is first get up to speed on a topic. Obviously, if you've got a textbook about what you're interested in reading about, that would be great. A lot of academic websites are really good too. Schools will publish stuff, faculty will talk about what they're doing, and that usually gets it to a level that you can understand. And frankly, Wikipedia is gets a bad rap, but it actually works pretty good. For science topics, Wikipedia is on par with the Encyclopedia Britannica. That information comes from the journal Nature. So get up to speed of what's going on. Obviously, filter out the really crummy websites. But once you get up a general idea, you can then start looking for review articles. I don't recommend jumping into primary research first. Eventually, maybe, but don't start with that first. You want to go for review articles. They're written a lot more like a textbook. They're a lot easier to read. They're usually written for someone who doesn't know everything on the topic, because if you knew everything on the topic, you'd be looking at the primary research. If you want to get there, you got a couple of choices. If it's more medical and based, PubMed, which is supported by the U.S. government, is definitely a great choice for that. Google Scholar, which is supported by Google, of course, is another great source of scientific papers, and a lot of them you can find free. A lot of them will ask you for $32 a copy. So, you know, I don't pay the $32 myself. I either get them through my library or I go find something similar that's free. But a lot of them, especially with recent changes to U.S. federal funding of research, you can get the paper and read it in the PDF form at no cost. Once again, if the paper you want is not one you can get for free, talk to your librarian. There's a very good chance you're going to be able to get to it without paying the $32. And I mean, you could pay the $32. I wouldn't, but that's up to you. And it's not always $32. It's sometimes more. Now, when you're reading a paper, and you get this one, if you're reading a primary research paper, which, once again, I would recommend reading the review papers first, but you can definitely read the primary ones too, especially if it's a well-written one on a topic that's not too obscure. And they're going to have basically the same general structure. They're going to start out, and they're going to have an abstract, or as Tom Scott calls it, spoilers. The abstract is a 1 to 2 paragraph summary under 250 words, usually 150 to 250 words, that summarizes everything in the paper. And quite often, even if you can't read the paper without paying the 32 or 45 or however many dollars, you can almost always read the abstract for free. And sometimes it's best to read the whole paper, but sometimes the abstract is really what you're wanting, because it's really a summary. It is the too long did not read for academic version. After that, you're going to have the introduction. That's a few paragraphs summarizing the previous work and how the author's work fits into it. Generally speaking, most research papers are written assuming that the reader has a bachelor's in whatever discipline is being discussed. So if it's a chemistry paper, it assumes the author has a bachelor's in chemistry but may not know anything about the specific topic or may not know a ton. So the introduction tries to catch them up to speed. Then there'll be materials and methods. Generally speaking, that's kind of dull. That's how you reproduce it. That's, once again, comes back to Boyle, where how the experiment was done. And this is, once again, usually kind of I skim over, I read that last. But it can have some really important details, especially where you see the study that studied a whole bunch of people, and then what you realize is a whole bunch of people was like 6. And so now all of a sudden you're like, okay, how much faith do I have in this study? They studied 6 people. But it can also tell you, no, they studied 6,000 people from all over the place, and you know what, I need to have some faith in the study. They did some good work. At least they appear to have done. The results, that's the data they have. Sometimes it's combined with the next part of the discussion, but it's basically what they found. Not the raw data, but kind of the core data they've got. It's been processed, but it's not, they don't tell you what it means. They just tell you what it is and then the results. The next part of the discussion, once it can be combined with the results, is the author's interpretation of what the results mean. How does that affect their hypothesis? How does that affect the model? Generally speaking, when I read those guys, I go for the abstract first, introduction, discussion, in that order. Then I usually skip the materials and methods and the results unless I'm particularly interested in going through them. So it depends on how much I actually care about it. Results are usually a priority over materials and methods. Once again, do I want to know, did they only study 8 people? Well, you know what, I need to read the materials and methods to find that out. Obviously, if it's not something I care that much about, I may just read the abstract. That said, you can do it. This is totally doable by the general public. It takes a little bit of effort to get it up to speed. Don't let it be that intimidating. Google Scholar, it's Google. It works beautifully. And then you can jump into these papers. Start with a review paper or whatever you're interested with, and then you can jump into the primaries. Take you a couple of hours to get up to speed, but a couple of hours ain't that bad if it's something you're interested in. Now, here's a couple of issues that we currently have. One, and this is kind of one of those, you got to make the cutoff. Nothing is known for certain. There's always dumb luck happens. Most research is analyzed using a 95% threshold, basically saying that there's a 95% chance that what I saw is real. There's always a chance that what you saw was wrong. It was complete dumb luck. So statistically, we figure out what the 95% threshold is, and if there is a better than 95% chance that what I analyzed was true and I didn't just screw something up, or some fluke didn't happen, then hey, it's good to go. But that does mean there's a 5% chance that something was wrong. That basically means a 1 in 20 research papers could be questionable because you don't know which 1 in 20. Ideally, what you do is you then have, or not you, but another researcher, completely independent, does the same experiment or a very similar experiment and sees if it works. Now, if you've been able to do the thing 2, 3, 4 times, you know what, it's legit. It's totally good. However, that doesn't always happen. Actually, that doesn't happen a lot. We're in what's called the replication crisis. The problem is that repeating somebody else's work is not all that attractive. It's not going to earn you great praise. At the best, you're going to hope for is to get a nice controversy when you say somebody else didn't know what they were doing. So it's not going to earn you great praise. It's not going to, frankly, make people want to hire you. So this is not just an ego thing, it's also an employment issue. And finally, people don't want to pay for it. Do I really want to go pay for someone to do something that's already been done? Why do I need to pay you? It's already been done. Well, you need to check it. So there's a lot lower funding. We've got a lot of issues with funding on replication, and that does mean that there is definitely some papers out there that we are building our model based off of. There are important model building research that are just wrong. And we're back to the same problem we were in the 17th century. Not to the same scale, by any means, but we still have that issue. And this is something that we as a society, we're starting to realize and we're starting to need to address. And we are starting there, but we've got ways to go. Also, there's publication bias, and this is not in the the bad way. Hopefully, there's no I don't like your data. It it conflicts with what I want it to be, so I'm not going to publish it. Hopefully, that's not true. Obviously, that does happen a little bit, but hopefully very, very little. That said, a lot of papers are submitted, not a lot are published. And journals are looking for a couple things whether or not they publish. And one of it is this an interesting? Will my readers care? Well, if it's not published, no one's going to read it. Let's just be honest. If you've got a journal and you publish a paper and it's water's wet. What I always like to describe as a water's wet paper, something that everyone knew was true, just never actually checked. Then the journal's going to be like, why am I going to wait to put this paper instead of some other much more interesting paper that changes the way we think in there? Well, the problem now is if 50 people study something and 49 of them find the very, very obvious thing that journals won't publish because they don't think the readers care about, and then one person finds some crazy thing, obviously they're probably wrong. You do it 50 times, 49 times you get one result, the 50th you get a different one. The 50th is probably messed up. Well, the one messed up paper gets published because that's the only cool one. It's the only exciting one. But now the world thinks something is wrong because the only paper ever published on this topic, because remember 49 were written but never published, says something crazy, and so everyone believes the crazy thing. We are working on preventing this by, once you set up certain types of experiments, mandatory publication. Additionally, not only will the journals reject it because it's not that interesting, the researcher will be like, it's not even worth my effort writing this. I know it's going to get rejected. No one's going to care. This is uninteresting. So we're left with several papers that have issues. Once again, though, we are working on this one, and we are trying to make this better. But this is an issue for the scientific community as a whole to start working towards addressing. So nothing's perfect. We've got issues. We're trying to address them. So be aware. And that wraps up our discussion on scientific communications. Once again, you can read the scientific papers. It's quite often a wise idea to don't just listen to the news anchor. You never know if they paid attention. Actually go to the research. Sometimes it tells a very different story than what the news spins it. So with that, I will see you on our fourth and final part, chemistry safety.